In this video, we're going to look at section 8.6 on power series, starting in page 128 of our workbook. So here we have a power series differentiation and integration theorem. Okay, so before looking at that, let's just recall the previous example we just did was example 4, where we were computing an integral of a function. And what we did here was say, well, hey, let's just replace that function with its power series, so this infinite sum, and let's just integrate term by term, and we'll be fine. So some of you might have thought, well, are we allowed to do this? Just stick in the power series and then integrate term by term, even though we have an infinite sum here? So that's a legitimate mathematical question. And it turns out, yes, we can do this for certain nice behaving functions. So in this theorem here on page 128, we are told which types of power series we can do that with. That is, we can compute which power series we can compute the derivative or integral of the function by just computing the derivative or integral of each term. Okay, so let's take a look at that. So it says, suppose f has a power series expansion given here. So the power series expansion looks like the sum of ci's or cn's, x to the n's, so that the series converges absolutely to f of x on the interval from negative r to r. So that's the case we're in, converges absolutely. So that means if you take the absolute value of each term and add up those, you're going to get convergence. Then for that interval, we have that the derivative of our function is equal to taking the derivative of each term of our power series. And the integral of that function is equivalent to taking the integral of each term of our series. And then, of course, adding up. Okay, so let's look at what that actually looks like. So we're going to write that out using some notation. So if we have that this series converges absolutely on some interval, then we know on that interval, the derivative of our function is equal to the derivative of each term. So let's go ahead and look at each term and compute its derivative. So derivative of C0 is just 0 because we have a constant, so 0. Derivative of C1x, well, would just be C1. Derivative of C2 x squared would be 2 C2x. Derivative of C3 x cubed would be 3 C3 x squared. Derivative of C4 x4 would be 4 C4 x to the fourth. So we can start seeing a pattern start to emerge. And we get that this is just equal to the sum from n equals 1 now to infinity of n times Cn x to the n minus 1. And so we see that come in. So like, for example, this first term, we have 1 times C1 x to the 1 minus 1, or x to the 0. Then next term for n equals 2, we have 2 times C2 x to the 2 minus 1. And so there's the pattern that we're seeing. So if our power series looks like the summation Cn x to the n, then the derivative looks like this here, the summation n equals 1 to infinity n Cn x to the n minus 1. Okay, and so similarly with the integral, though, we're going to be able to integrate each term. So when we're computing an integral of such a function with a power series that converges absolutely on some interval, then that integral, how we compute it is by just taking the integral of each term, or that antiderivative of each term. So what does that look like? Well, the antiderivative of C0 is just C0x. Antiderivative of C1x is just C1 x squared over 2. Antiderivative of C2 plus x squared is going to be C2 x cubed over 3. Antiderivative of C3 x cubed would be C3 x to the fourth over 4. And we'll just write out one more term, C4 x to the fifth over 5. And so now notice we don't have bounds or limits on this integral. So this would be a general antiderivative. So in the end, after we do all this adding up, we should have a plus kind of c, a generic constant. But just because that's looks kind of odd having an infinite sum and then plus c, we're just going to go ahead and add that constant to the beginning. Okay. So then we can write this a little bit more cleanly. So we have that c. Always remember the plus c for the arbitrary, not arbitrary, but for the constant given by a indefinite antiderivative or integral, indefinite integral. And so now we can see that the terms look like, well, we start with n equals 1, and then, or actually we can start with n equals 0 and then add 1 to the exponent. So here, if we said n equals 0, then we get 0, c0, x to the 1. Here, if n equals 1, we'd have c1, x to the 1 plus 1 over 1 plus 1. And so what pattern we see emerge, it looks like the sum of n equals 0 to infinity of cn x to the n plus 1 over n plus 1. So if our power series converges absolutely on an interval, then the integral of that function is the integral of each term of that power series, and it'll look like this form. So what's really cool is that we can go ahead and just use these two forms whenever we're asked to compute a derivative or an integral of a series or function that we know has a power series that converges absolutely on an interval. Pretty cool stuff. And we'll see some examples of where we will use this.